All right, so a lot to get through today. So let's go ahead and move forward. So reminders, homework C2 is due Saturday. That's on random number generation, which we actually talk about today. Homework D2 has been posted, so that's on random-VARIATE generation. So a couple of tips to do a little bit of calculus on it. Both of these, by the way, serve as exam practice, but when you're doing that integration on that first problem, remember that when you integrate with limits here, if it's a piecewise function, you have to break the pieces up. And if you want to see examples of this, I've posted a bunch. Just click on the homework assignment and read through the assignment, and there's some links. I've got some video links. I've got some example problems that I've sort of already worked that look like this. But the TLDR of it is, like, for example, if you have a piece of your density function that goes from negative infinity to 0, and another piece that goes from 0 to x, then it's legal to break this integral up into those two separate pieces and adding them together. And the reason you want to do that is if you're in the second piece, you have to remember you can't just take the antiderivative of that second piece. You have to include the whole contribution from that first piece. So as you start moving up into those other pieces, because you're integrating from negative infinity to 0 or to wherever you're integrating to, you have to accumulate the full contributions of those previous pieces, even if that's not the piece that you're currently taking the antiderivative of. So that's, that is something which, again, I've got examples online, and then we'll talk about that next time as well. In the second question, you're going to have to invert a square. And when you invert a square, remember, when you think of the square root, basically, then you can have a positive square root or a negative square root. And so either one is mathematically legitimate, but they're not always statistically legitimate. So when you take that inverse to generate your random-VARIATE generator, you have to ask yourself, what's the range of this random variable? If I were to choose positive here, will that put it inside my desired range? If not, then maybe I should have chosen negative instead. So those are just some tips. They're talked about in the homework assignment. We will talk about them more explicitly next time. There are also examples that I've done online that are connected to this homework assignment on Canvas, so you can find those tips in as well. So just highlighting that those are kind of the two big things. Question 1 is really about making sure you know how to do this, breaking this thing up. Question 2 is a lot about making sure you know how to choose the right sign here. Those those D2 are due next Saturday. And so when you generate these random variates, you're probably going to drop the formulas that you generate into something like Excel or MATLAB. But let's say you drop them into Excel and you're going to generate, I forget how many, maybe I say 10,000 random variates. And then I ask you for a histogram. The histogram should go into your, say, Word document or Google Docs document that you use to build your response to your homework assignment. That's the kind of what should be the main response. I'm going to ask you to sort of, as part of showing your work, if you did use like a spreadsheet to generate those numbers, to upload the spreadsheet too, but that doesn't really count as your answer. So the histogram in the document is what we're looking for. So don't upload to the TA like just, like what I've had students do before is they'll take their spreadsheet and they'll effectively pull it into the doc where they'll just upload their spreadsheet, and it's like 25 pages of numbers. And that's their answer. And that's asking the TA to do his own histogram and figure out if they're the right numbers. And so that doesn't really count as an answer. So we're looking for that histogram that confirms that you actually drew samples from the right distribution. And so that's what I mean down here. So don't just submit a spreadsheet with thousands of random realizations. Think about if you were giving this to your boss, like things that would get you fired, do not submit those things here. So pretend like I'm a stakeholder or your boss. If a stakeholder would just throw whatever that is away and seek another company, then that's probably not what you want to submit as your homework. Okay. So otherwise, ICAF, remember this is now available. This is like a midterm practice ICA. So rather than being a lot of new content, it samples randomly from the previous ICAs, and you can take it as many times as you want. It'll give you the highest score that you receive on this. Because it's sampling from all of those, it is a little longer than a normal ICA, but it's meant to be practice, and it's not timed, so you could start it and come back to it and things like that. So unlimited attempts, grade taken from highest score. Midterm soon. So this is lecture E1. We have lecture E2 on Tuesday. We have the midterm review space on Thursday of next week, and then the midterm is the week after that. So, see Canvas for helpful resources. There are sample midterms. There's the midterms from previous years. In order to access that midterm module, you have to do the lockdown browser compliance module, which is basically just you take it's a one question dummy quiz just to make sure your lockdown browser is working. And once you take that, and that actually gives you a small fraction of credit towards the midterm. And once you take that, then that will unlock the midterm module. And that's where the midterms will end up being posted. But it also has all these resources. So all of the study guides and the practice exams and so on. So that's how you get into that. So, and I've talked about it's a stage 1, stage 2 setup. Talked about that. We've got a lot to talk about today, so I'm not going to belabor that for now, but we'll revisit that during lecture F, and there's more information about this online. But I'm happy to take questions about that here in a second. But let me get through the rest of these assignments here, or announcements here. And then I mentioned now that we're in lab 5, and a lot of the lab assignments will be based off of book assignments, but I've given you easy access to old versions of the lab textbook online. And so those hopefully will be okay in case you don't have an easy access to the latest version of the textbook. But you do need some access to one of those books, probably 4th edition or higher. Yeah, any questions? Yep. If you go to Canvas and go to the modules, I think just under the course information module, there's like a textbooks module. And I think if you open that, I think I've got links in there to access those. Any other questions? Okay, great. So last time we set up probabilistic modeling. So remember our key motivation, we're building stochastic models. So we have to use probability as a tool for modeling the real world. And so those probabilistic models are our so-called input models. So before we can get variation on the output, we need variation on the input. So that variation comes from random sources of variation from the real world, like arrivals to our systems, failure distributions, failure time distributions to our systems, demand distributions. All these things are random inputs that you can look up in a table that have been statistically characterized by someone else, and you pull those in and you dump them into your sim. And then in your sim, you say, now that we have all of these inputs to our systems, we're going to do things with them. So we're going to combine them in different ways. We're going to sequence them differently. We're going to do our engineering about processing these inputs, and then we're going to generate outputs. The outputs will be random because the inputs are random. So we have to choose the right inputs there, and that's why we have to, know about these probabilistic models, because that's really how we get variation into our system. So we talked about last time, there's a core set of kind of Lego bricks that you should have available at this point in your career. And as you move on, if you do more stochastic modeling, some of these gray ones will end up being more useful as well. These are ones that I use as well, but the kind of these bold ones here, uniform, triangular, all of these down here, these are all the ones that I'm kind of counting on you to have at the end of this class. They're kind of like the fundamental building blocks of probabilistic models, of stochastic models. And as we talked about last time, there are certain situations where you'll want to use each one of these. For the midterm or for the final, I'm not expecting you to memorize a probability density function for each one of these, or a cumulative distribution function for each one of these. If we were to do that, there are tricks that I could teach you, like the normal distribution. It has kind of an ugly looking PDF, but if you know how to break it down, you realize, oh, it's just a radial basis function with an exponential decay. Like there are ways to sort of break those things down. So there are ways to learn those things, but sort of beyond the scope of this class. What I'm trying to get you to for this class rather than memorizing what the PDFs and CDFs look like. And likewise, you've got these notes sheets. Like you can have two-sided pages of notes for your midterm, your stage one. I don't think you should waste a lot of space unless it helps you to see the structures, writing down the PDFs and the CDFs. I'm not going to quiz you on those structures, but what you should know are when you might want to use a uniform distribution or an exponential distribution. How might you rank those? So based on information that your stakeholder's given you, how might you decide that, based on what this stakeholder said, probably the uniform isn't the best choice. Maybe I need to do a normal for this. So that's the sort of stuff I want you to pick up here. So I gave you the PDFs and CDFs because we need those in order to load them into the computer, but don't worry about memorizing those for the midterm, but do worry about, this idea of when do I use each one of these? And that's what we talked about last time. What we stopped at last time so these are random variables. And so we stopped last time at random processes. So I want to cover that real quick so that we have the Poisson process. So as I started to talk about last time, a random process is an index family of random variables. A simple, I don't want to say simple as trivial, but a kind of basic example of one of those is what we call a counting process. And so what a counting process is it is a collection of random variables that represent the count of things up until a particular time. So you could say each one of these n random variables here, so n at t for some t, we could say, well, that represents the count of, say, events that have occurred up to time t. But a counting process collects all of those together. So it doesn't just tell you that, like, well, for this hour, what's the count of failures that have occurred? It then collects all those together to say, for any time you give me, I can give you the random variable representing how many failures that have occurred up to that time. And by collecting all of those together, we not only can talk about how many failures have occurred in a time, but we can actually then talk about the time between failures as well. So it allows us to talk not only at one time, but then compare across times. That's one of the things that a process does for us. So it's just a family of related random variables. And the one that you'll see a lot in this class and in a lot of your other classes that use stochastic modeling, particularly 470 queuing network classes, is the Poisson process. And a Poisson process is a counting process, but it has some special constraints. So one thing is it's modeling the count of, in this case, we'll say the count of arrivals or the count of events up to a particular time, like any other counting process. But there's no simultaneous arrivals in a Poisson process, or they happen with probability 0. So other counting processes may allow, but there could be a 10% chance that that the count increases by 5 at a particular time. That won't happen in a Poisson process. Poisson process, at most, probabilistically, at most, you get one encounter at any instant of time. It is possible to get more, but they happen with probability 0. So then there's what they call stationary increments. And so the idea here is the distribution of arrivals between two times only depends on the distance between them. So what I mean by that is if you were to say, well, what's the random variable for the count of arrivals at time 1, and what's the random variable for the count of arrivals at time 6? Well, the 1 and the 6 don't matter so much as the distance between them. Or if I were to say that another way, if I want to say how many new arrivals did I get between time 1 and time 6, that only depends on that time between them, 5 seconds. So if I want to describe the new arrivals, it's just that it could be between 6 and 11 or 11 and 16. It's that distance between them. It doesn't matter where we are in the timeline. If I want to know how many more arrivals have I gotten in a particular increment, only the length of the increment matters. That's another key feature of a Poisson process. And independent increments. And so what this means is that if I have non-overlapping time intervals, so I want to say how many arrived between time 1 and time 6, and how many arrived between time 11 and time 24. The knowledge of how many arrived in one increment does not reduce my uncertainty about another increment. So there's no relationship between outcomes in non-overlapping intervals. And that's what we refer to as independent increments. So knowing the count at one time does not change the probability distribution of the count at another time. Those are the key features of a Poisson process. Questions about those definitions? So if we know all of that, then a bunch of nice math pops out. So one of the things that comes up is that, and so we're going to say a Poisson process with mean rate lambda. So that's how we're going to talk about this. So we always associate a rate or an intensity with a Poisson process. And so if it has all of those properties and it has this rate lambda, then the actual distribution of the count at any particular time will be Poisson distributed. And that's all we're saying here. And so this is a discrete random variable. And so we're saying that the probability of any particular count at any particular time is according to the probability mass function of a Poisson random variable. So counts are Poisson distributed at any individual time. So the mean of the count at any particular time is going to be equal to the intensity lambda times that time. And this generalizes to say the count of arrivals in any increment, in any inter-arrival duration. So if you know, like, well, okay, so it's time 6 now, it will be time 11 later. So there's a 5-second gap in between them. If I know that 5-second gap, that 5 seconds times the intensity will give me the average count for the Poisson random variable that will represent that increment. So that's a key thing that we know. The other thing is that so this is discrete. The continuous thing we know is that the time in between arrivals is exponentially distributed with that same rate. So for 2 arrival times, then that are sequential. So for arrival times A and B, where A happens before B, then the probability, and these are, for sequential events, there's no other events in between them. So I've got an arrival at A, which happens before the arrival at B. And so for those, I can say, what is the probability density function representing the time in between those times, the time in between those event arrivals? And that is exponentially distributed. And so the average time is 1 divided by the intensity. So if you arrive at 5 people arrive per hour, then the average between them is going to be 1/5. So 1 person per, so 5, I said 5 per hour. So if you flip that around and you say, well, so 1 hour, we get 5 people. So that's a 1/5 of an hour between every person on average. And so those are strongly related there. And because of that, when you're first learning this, a common error we see is that students will get confused about which an exponential being a Poisson. So I'll ask, like, what's the count of, how is the count of arrivals distributed? And the brain will go towards exponential because we hear exponential more often. But they're related, but Poisson is always discrete. Exponential is always continuous. So that's a key thing to remember between these two. So exponential is the time between arrivals. Poisson is the count of arrivals in a time. Any questions about that distinction? And both of these are bundled together in a Poisson process. Okay. There in lab 6, we will talk about scheduling in Arena. So in lab 5, as you start building your first models in Arena, you'll see that you can schedule arrivals. You can say these customers arrive or these parts arrive at a particular rate, and that rate is assumed to be constant through the sim. But in lab 6, we'll see that we can actually change that rate throughout the sim. So we can say in the morning, there's this arrival rate. In the afternoon, there's this arrival rate. In the evening, there's another arrival rate. And that's what was called an inhomogeneous or non-homogeneous Poisson process. So it has a time varying intensity, a time varying lambda. So that gives us a lot of power to model a lot of arrival processes. So not very few real arrival processes meet all of the definitions of a Poisson process. But when you allow the arrival rate to change, then everything ends up being much easier to approximate as a Poisson process because you can zoom in. You can say, okay, so over the day, it's not a Poisson process but if I zoom in and model it hour by hour, every hour's arrivals is almost a Poisson process. So I just have a different rate for every hour. So when you're modeling, so if I have, I've had students work on projects for me where they go to the airport and they model things at the airport, and they can't model the entire arrival process at the airport with one model. But they can break it up and they can say, well, I noticed that there's, it's pretty busy in the morning. It's not so busy in the afternoon. It's pretty busy in the evening. So they might start modeling, like they'll take data for every hour, but then they'll notice that the first 4 hours of the morning, all of the hours look very similar together. So they pool them together into one morning arrival process. And then they do something similar for the afternoon hours. So you might start taking data at hour resolutions. Then you might find you can pool them for a better statistical model, but you just have to make sure that you're not pooling, P-O-O-L, pool. You're not pooling together too many things that have different arrivals or different arrival rates. But if you break things up into fine pieces, then often you can approximate them with the Poisson process, which makes them a very powerful modeling tool. Any questions on that? And again, things that hopefully you'll see repeated in like a course like 470, because we often assume this process in order to build queuing network models. Okay. So two other things that again you'll see in 470, but you'll also start seeing in your models. And I bring these up not because I'm going to quiz you exactly on these, but as you're building your models, like for your final project or whatever, this shows you how you can have flexibility and the choices you make in developing these arrival processes. Because if you start with a Poisson process, then if you split it, and what I mean by split it is like you got an arrival block, so your customers are coming in, and then you can put them into an arena, what you'll find is a decide block. So it's a fork in the road where a certain fraction of individuals go to the left and the rest of them go to the right. When you do that, the two split processes that come off will also be Poisson, but their intensity will be scaled down by the probability that you split them. So if you've got 10 arrivals per hour coming in and you split them, so half go one way and half go the other way, then you're going to have 5 arrivals per hour going one way and 5 arrivals per hour going the other way. And those happen to meet all of the assumptions of a Poisson process. So you can break Poisson processes up and you still get Poisson processes, but with these rates coming out. So as you're building your models, you can say like, maybe I'm going to generate a bunch of customers and then tag them with attributes later and then split them by their attributes up. That's one way to do it. Or you can say, well, since I'm just going to split them up anyway, I'm just going to create separate arrival processes for each of my groups that I was going to split up. But they'll have different rates. Either one of those works fine, because if you split, it's still Poisson. So that's a really nice property when you're doing your modeling. Gives you a lot of flexibility. Likewise, the flip side of that also works. So-called pooling of Poisson processes. If you've got a bunch of Poisson processes and they come into a junction and they join together into one big process coming out, that process will be a Poisson process where you add all of the intensities up together. So 5 arrivals per second or 5 arrivals per hour plus 5 arrivals per hour, they come into a junction. It's now 10 arrivals per hour and it's still Poisson. So it doesn't violate any of the Poisson assumptions. So this is part of the reason why in classes like 470, you can build queuing networks out of Poisson processes. All right, questions about that? Okay, So now with that, this is sort of your new sheet of the things that I want you to make sure you know. I don't need you to know the PDFs or the CDFs specifically, but I want you to know, like, the light colored ones, those are the things that hopefully if you continue to do this more in your career, you'll pick those up. But the ones that are kind of in normal type, the red ones, the blue ones, and the green ones here, those are the random variables that I want you to know when to use that random variable over another. And then the Poisson process, which, because we're dealing with dynamic systems, this is like our way of modeling how random variables can change over time as well. So those two things together, those are our big blocks that we use to build our input models. All right, so that's our review from last time. Any questions? Okay, so we've got random variables. So once we've chosen a probability distribution, then a question is, how do we get the computer to now generate samples from that probability distribution? So, we've got our input models, like X is a lifetime of a device that inspects cracks. Failure times are exponentially distributed. How do we get exponentially distributed failure times? Excel does not have an equals expo, nor does Google Sheets that will give you those exponentially distributed failure times. Arena does, fortunately, it does some of this work for you, but you might end up developing a random variable that isn't in the database. So then what do you do? And so we talked about that, and we'll talk about this more next time. If you have the probability density function for that random variable, you can turn it into the cumulative distribution function by integrating under it. And then that will give you something that is, that is rising or S-shaped, like this cumulative distribution function here. And once you have that cumulative distribution function, as you'll do in this homework D2, once you invert it, then it turns it into a random variate generator. And so the way that random variate generator works is if you have a random number generator, which generates numbers uniformly from 0 to 1. So notice these are equally spaced on the y-axis. Because I've inverted it, then I'm taking the inputs on the vertical axis and the outputs on the horizontal. So, I'm flipping it along the diagonal. Even though these are uniformly distributed, when they map through the inverse CDS, something we'll call the quantile function, then they get spread out. And so they get clumped near 0, and they get spread out towards infinity. So they're not very dense. You don't get many outcomes out here. Most of your outcomes are here. And that recovers the original probability density function that you wanted. So that's how we're going to do that next time. But that requires us to have this to begin with. So how do we get, so this is what we're going to end up getting out. How do we get the uniform random numbers to begin with? That's something that we do care about implementers in the computer giving us a good source of uniformly distributed random numbers between 0 and 1. So how do we get that? If we haven't been given one that we're satisfied with, how do we build one our own, which sometimes you have to do. So this was a big question that around World War II, they were starting to develop the atomic bomb. They started to need computational power to start really cranking through predictions before they could build this thing. And that's actually where Monte Carlo analysis came from. But in order to do Monte Carlo analysis, the subject of Lab 3, they needed to generate random numbers. And so people like von Neumann, who's it's one of the kind of the people that sort of are responsible for modern computing, were involved in trying to come up with the first uniform random number generators. And von Neumann had some hesitation at this. As a quote, anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. And I highlight that because it turns out that there were a group of people that were working on this problem years before the scientists working on the atomic bomb were working on it. And they were, as we'll see, they're down here, they were actually Franciscan friars. So they were monks who are working on this problem. So people have been interested in this problem in a long time. There are weird sources you might think. So you can go to Amazon and you can buy a small book of random numbers. And inside of it are pages of random numbers. So once upon a time, this actually was a way that people generated random numbers. In the 70s and the 60s, if you needed a string of random numbers to put into a process, there were textbooks, there were CRC manuals and things like that that would just have random numbers that you could trust were uniformly distributed. And so people did that. But that's not that practical nowadays. We call up MATLAB or Excel, and Excel, we've got a rand function or rand between, and MATLAB, we have a bunch of rand functions. And that's great. That's much more convenient than looking them up in a book. But is it a reliable source? That's really our question. What does it even mean to be a reliable source? So with that in mind, over time, we've figured out that there are sort of two properties that we care about in a random number generator. And it should make sense. They're the same two properties that you care about when you're building a 20-sided dice. So, what would you say is an important property for a dice or for a die? Like, what do you want to be sure? So equal frequency. So the idea there was that each face of the die shows up equally at the same frequency as every other face. So that would mean it's uniformly distributed. So we want uniformity. What's another property that you might want of a random die? This is a little harder, but you're sitting at the tables in Las Vegas and you're watching somebody roll a die. If you're watching someone else roll a die, certainly what would the people who own the casino want to know about that die? What do you mean by independence? Each roll is independent of the others. You don't want to be able to predict the next die roll from previous die rolls. If somebody rolls a 6 and rolls a 7 or something like that, if you look at that pattern, you don't want someone else watching to be able to then be able to predict the next one. I mean, they might be able to tell that, it only goes from 1 to 20, but they knew that ahead of time. So, but now that you've watched the sequence, you can't say, I think there's going to be a 9 is more likely coming up next. So we want that. So that's what we want, uniformity and independence. So every outcome is equally likely, and every draw doesn't give you any information about the next draws. So, we define those formally here. So for a random number, so this is a distribution 0 and 1, we want to make sure that its probability density function looks like a uniform distribution. It's flat from 0 to 1. So likewise, we want its expected value to be right there in the middle, 0.5. So the one way we can test that is if we divide the interval 0, 1 into subintervals, then we basically turn it into a discrete die face. And we want then the outcomes to be no more, any interval will have no more than big N, that's your total number of rolls, divided by n subintervals, how many subintervals you divided it up by. So if you have 100 rolls and you divide the interval into 5 groups, so 0 to 0.2, 0.2 to 0.4, and so on, all those 5 groups, then we'd expect to see roughly 20 outcomes in every bin, in every group. That would be an expectation there. So, an example for our 20-sided die, a good 20-sided die would be this top string. If you look at this top string, there's no numbers that are repeated or no ranges of numbers that you see more than any other ranges of numbers. But this bottom string is a bad example because you keep seeing 2 showing up over and over, maybe numbers near 2, maybe 2 and 7. I see a lot of 7s. I never see an 8. I never see a 9. So these are examples where it's, it looks like it could be uniform, but when you actually do the rolls, it isn't. It's not a fair die. That's what I mean by uniformity. Questions about that? And this property here, if we divide it into n subintervals, that will be very important because that's going to be one of the key things we use to test whether we have uniformity. Okay, and then the other half of that is independence. So we want to make sure that they're independent. So the probability of any later value is independent of any former values. So an example of that is a good die roll. This top one here, there's no pattern. But the bottom die roll, the numbers are counting. It is uniform, but the numbers are counting up. So if I know that the previous roll was a 5, then I have a good guess that the next roll is going to be a 6. Or even if I just know that the next roll is going to be higher, then I'm in better shape than I was if there wasn't this pattern. So on a midterm, I might show you, strings like this, and I might say what property is violated here. And you could say, well, that looks like it's violating uniformity. That looks like it's violating independence, or that actually doesn't look like it's violating anything. That looks like it's pretty good. So, hopefully you can spot that. So is it clear to everybody why this is bad and why this fits under the category of it is not independent? Okay. So we're going to test for uniformity and independence when evaluating our random numbers. And I'm going to skip the clicker right now just to make sure we stay on time. Okay, so throwing dice, like this is one way to do true random numbers. I've mentioned that before. Not very practical computationally. There are a bunch of other ways to draw true random numbers. You can draw from a shuffled deck of cards. You can draw a ball from a bucket of balls, a well-stirred urn. Some online random number generators like put up a lava lamp, and they take an image of a lava lamp and they do what's called a hash function. So they basically take all the pixel image number, like they create numerical data out of all the pixels, and you can effectively think of them adding them together and creating a random draw from those pixels. And that's another way to draw a random number. You can go to random.org. So a lot of scientists that I know that are setting up tabletop experiments, they often have to randomize. Like if you've got 10 subjects that you're working on, so 10 mice or whatever, and need to randomize the order of treatments, then they'll go to random.org and have it draw a random order for them. Say, or do mouse 1 first, or maybe not 1, maybe 9 will go first, and then 1, and then 2. And that order comes from random.org. And random.org gets its random numbers by sampling from atmospheric noise. So it looks at little like pressure variations around a sensor that random.org has access to. So those are all sources of true, I guess, randomness that we get from the outside world. There are fancy computers that have ways to use the heat inside the computer as a source of randomness as well. These are not often practical sources, though, for computer simulation, because we might need to draw on one computer simulation, 1 million random numbers, and we need to do that very quickly. So we can't just be going out to random.org and getting each one of those numbers. We need to do that fast. So there are certain desired features that we want in our random number generators. So fast, that's one of them. We also want them to not repeat after a sufficiently long cycle. So once we abandon true randomness, we probably are going to use a mathematical function to generate random-like numbers. But that probably means that it has a tendency to repeat eventually. And we want to make sure that that sequence only repeats after a very long cycle. So we can get 1 million, 2 million, 1 billion numbers before we start seeing the same cycle start over again. And then the other thing that it doesn't seem like it'd be something that we might want at first is we want repeatability. So although we want it to be apparently random and have a long cycle, we want to be able to seed the random number generator so that you get the same cycle or the same numbers out if you start from the same seed. So this is like having 5 die or 5 dice in a drawer somewhere. And when you pull out this one, you get 1 million, a sequence of 1 million numbers out. And you pull out this one, you get a different sequence of 1 million numbers out. But if you pull this one out again, you get that same sequence of 1 million numbers that you originally got out, and likewise with this one. That repeatability can be valuable because it allows you to rewind the universe and play it back. So if you can play a simulation forward, then if you notice something interesting happened, but you didn't gather enough data, then you can replay the universe from that same initial condition, from that same seed, but now put more measurements in play. So it makes it much easier for us to investigate. And it allows us to do things like we did in the muffin sim, where you can give the same random environment to two different models and study them with the exact same inputs. So it actually improves our statistical ability with these models as well. So that's another weird idea here. The other, but it's really important. And the other thing about it being portable. So sometimes, like, you might show your boss that, oh, I saw a failure mode that we've never seen before in the simulations, but this is a simulation of a nuclear reactor or whatever, and it's a failure mode that we should have been able to catch, and we really maybe need to put in safeguards for that. And you want your boss to review it. Well, if it was just truly luck that caused you to find that failure mode, it may be very hard to get that back. But you can say to your boss, well, run the sim with this seed, this random number seed, and then your boss can look at that failure mode and investigate it for them. So it allows your results to be more portable, and not just from you to your boss, but it might be that someone else wants to repeat your work, to check your work. If you run it on this computer, you want then, this is a Mac or whatever. If you take it to a Linux machine, you want also to get the exact same results when you run the same seed. So you're not seeing something that's an artifact of the computer. You're seeing something that is coming from something that we've built into it. So we're more confident that the model results are real and not artifacts of the platforms we run them on. So those are properties we want. But if I ask you on a midterm, what are the two required properties of a pseudo-random number generator, even to just make it to market? It's uniformity and independence. It's not these things. These are desired properties. These are properties that we would like to have. In order for them to be marketable, in order for them to gain market share, they should have these things as well. But in order for them to even make it to the market, they need these things. So these are the required features. These are only desired features. Questions about any of that? Okay. So in Excel, seeds are chosen internally. So if you open an Excel spreadsheet that uses random numbers, if you open it at a different time, you'll get different random numbers. And that's because Excel doesn't allow you to adjust the seed. It just picks the seed using the current time. So the current time becomes its seed, and that's what generates the randomness. That's not very useful for us in running computer simulation. So that's why in professional simulation tools like Arena, you have the ability to adjust the seed. And so you'll have a chance to play with this in different labs, but basically there's an element, a seeds element that you can open up in Arena, and you can create your own seed, or you can get information about the seed that was used. Any good simulation program will have a way to tell you what seed it used for every replication of your experiment, and have the ability for you to change it. And that goes back to the properties that I was just talking about. Okay, questions? All right, so those are the properties we want. How do we build a random number generator with those properties? And this goes to things that you're going to be doing on that homework that's due this weekend. So one of the earliest attempts, and this was first described by, again, Franciscan friars. It was reinvented by von Neumann around, when they were advancing nuclear technology. The method here, and this is not what we use today for reasons that we'll see in a second here. The method here is to start with 4-digit positive natural numbers, and that's going to be a seed, like 1, 2, 3, 4, 7, 8, 9, 10, or 7, 8, 9. 7890. So 4 digits. You start with 4 digits, square that seed to form an 8-digit number. And if it's not 8 digits, it usually will be, but if it's not 8 digits, then put zeros on the front end to pad it up to 8 digits. If somehow it goes over 8 digits, then just cut it to 8 digits. And then set the new, I don't want to call it the new seed, but the new internal latent variable to be the new 4 digits in the middle of that number. And then take that, and that becomes your random number, those 4 digits divided by 10,000. And then repeat this process, substituting those 4 digits for the previous seed. Do that over and over and over again. That's the so-called middle squared method. It was trying to get a chaotic pattern out, a near random pattern out. And you get results that look like this. So you start with 5197 as the seed up here, and you go through that process. Here's the random number that comes out of it. The downside here is, although you're getting different numbers out, it decays to 0. And you just then at that point get 0 over and over and over again. This is not a good random number generator. It's clear there's a pattern here. It's clear that it's also not uniformly distributed between 0 and 1. So that's not good. You can try different seeds. So this seed, 6500, you put that in the middle and you get the same random number out over and over and over again. So that's also not good because it's has no independence and no uniformity. Uniformity is sort of the biggest problem here. Other seeds, you might start out okay, like you start out with these kind of unique patterns, but then you get stuck in cycles. And here's a cycle of 4 numbers that repeats over and over again. And sometimes it's really hard to detect those cycles because you can start with a seed up here, and then you get this long transient, and that long transient here ends up eventually leading to a cycle. So the 84th number, we start a cycle like this cycle, but we had to go 84 numbers to even detect that that cycle was there. So that's really scary because it suggests that you might start out and you might think your random number generator is working fine, but it might be 3 million numbers in, you get into a 3-number cycle. And so suddenly your sim starts acting funny because you end up getting the same 3 customers over and over and over again, but you didn't detect those same 3 customers until 3 million customers in. So that's not going to work out. So, the pros here, it's simple to implement. That's basically all the same. Simple to implement, it's fast. It's difficult to choose a seed. There's a tendency to decay to 0 and you get short cycles. And a bunch of their other attempts at pseudo-random number generators had all the same problems. So this was not great. Finally enters in a little bit later, maybe in the 70s or so, linear congruential generators, LCGs. This is what you implement on your homework C2. An LCG has the ability to have all the features we want, and even some of the desired features. So it has all the features we need, and it provides a pathway to the desired features. And this is what, again, you're going to practice using on your homework and maybe on the midterm. So the parameters here, the idea is you got these 4 parameters. You have your seed, like any random number generator should have, what's something called the multiplier, an increment, and the modulus. The way the method works here is we have this formula where the next number is just going to be the previous number times the multiplier plus the increment, and then that whole quantity through the modulo m, where m, this modulus, is kind of like the highest number you could possibly get plus 1 out of it. So this would be like if this was, if we set our modulus to 10,000, then this formula would give us numbers from 0 to 999, 9,999. And so remember, mod here is the remainder. So what this is doing is saying, generate a number which may be bigger than 10,000, divide it by 10,000, and return the remainder. And that gives us a number between 0 and, again, 1 less than the modulus. So then that allows us to divide by the modulus to give us a number between 0 and 1. That's the idea here. That's the linear congruential generator. It has other names. It's got the mixed congruential generator. That's when C is not equal to 0. If you set C equal to 0, sometimes it's called the multiplicative congruential generator. There's a bunch of other names. I'm not going to quiz you on the names, but all coming back to basically the same idea here. There are nonlinear versions, so we do a little inverse here instead. But this does a pretty nice job. At least it does a basic, it does the basic things we want. We have to modify it to get long cycles. That's what we'll talk about here in a slide or two. Now, one of the cool things about this is you can do math on it. And you can prove that if these things hold, and I'm not going to quiz you on these conditions, but you have to know that there are conditions that if you set up these parameters correctly, and I list the conditions here, then it guarantees that this little iteration will have a full period. That means that if your modulus is 10,000, you'll get 10,000 unique numbers before it recycles. Not unique numbers, but a pattern of, you'll get a unique pattern before it recycles. And so that's a nice feature. You can guarantee the full period. You don't have to speculate like you had to with other random number generators. Just set things up this way. So here's an example of that. This is just like the example you're going to do on that first part of the homework that's due this weekend. I give you a seed. I give you these, the multiplier, the increment, the modulus. And so you plug the seed in. The seed times the multiplier plus the increment, that whole thing, mod 100. And so it's 502 mod 100. You take that, the remainder is 2. 2 divided by 100, 0.02. So that's applying the method. So my first random number is 0.02. I want to emphasize this because this comes up in the midterms sometimes. You don't use the seed to generate your first random number. So the seed was x0, x0, but I used x1, which was a function of the seed to generate my first random number. So the first random number is after you run the iteration through once, then you get a random number out. You don't use the seed to generate the first random number. So then I do that again. I take this 502, that mod 2, so I take the 2 here, I plug it in the same spot where the seed used to be. I do it again, I get a new random number, and then I do that again. And that is my linear congruential generator, and here are the random numbers I'm getting out. Questions about the LCG? Yep. Yes, 100%. So one of the downsides of having a full cycle is you aren't going to see the same number again, because if a full cycle is 10,000 numbers and all you have is 10,000 numbers, then if you land on a 6, then that 6 is always going to be followed by the same thing. And there's no chance, like once you see a 6, you'll never see a 6 again. So that's something that we need to fix, that we're going to fix in the next slide. Great question. Good eye. All right, not the next slide, next like 2 slides. So, so this is an example here where you can get very long cycles. So I didn't set this up to have a full cycle, but still I got 2,000 numbers out until I got a repeat. But as the point was saying, I know it's a repeat because once I get 468 again, there's no chance. It's a deterministic thing. It's going to run through the same cycle again. There's no way to get 468 and not get the exact same cycle again. So that is an issue that we have to deal with. But we're getting uniformity, which is great. We're getting independence at a small scale. But at a large scale, once I see the first cycle, I know what the next cycle is going to look at. So that could be an issue. So a solution to that issue is the so-called combined LCG, the CLCG. And this allows us to get much, much longer periods with repeats. And so all we do here was we take 2 LCGs and we, with a different modulus for both. So this one might have a modulus of 100, this one might have a modulus of 1,000. So we have 2 LCGs with different moduli, and we add them together and then take that mod, our new modulus here. So as an example here, so this is a published example. Here's one linear congruential generator. Here's another linear congruential generator. These are just multiplicative. They don't even have an increment. You combine them into a combined linear congruential generator. This thing's got a gigantic period. And there's now ones that have even bigger periods. And what's nice is if you look at how they work, so here's a simpler example that I built. So I've got one LCG down this column, another LCG down this column. This one has got a period of 4, 1, 2, 3, 4. This one's got a period of 3, 1, 2, 3. So when I multiply them together, this, not multiply, sorry, when I add them together, then I get sort of a beat that is formed and allows me to get this undertone of a period that gives me a period of 12, so a much bigger frequency. And the cool thing about this is now I get, so here's a 1, the 1 shows up again, and now the 1 shows up again, and now the 1 shows up again. So now in this output, I get the repeats. So if I see a 1, for over here, if I see a 1, this 1 is always followed by a 2. This 1 is always followed by a 2. This 1's always followed by a 2. This 1's always followed by a 3. But over here, when I see a 1, there's still, if I watch this for long enough, I eventually, once I see a whole cycle, then I'll know that a 1 will sometimes be followed by a 2, sometimes be followed by a 0, and I could catalog all those up. But if it has a cycle of 10 to the 18th or 10 to the 80th, I mean, there's now really long cycled ones. I'm probably not going to be able to get enough information to be able to figure that thing out. So that's a combined linear congruential generator. It gives us very, very long cycles that allow us to have repeats. So it improves our independence significantly while maintaining uniformity. Questions about that? Combined LCG, CLCG. Key thing to remember is, how to do an LCG. The rough formula for how you create a combined LCG, you just add or subtract two LCGs, and the purpose for generating a combined LCG. Why is an LCG not enough? The short periods and this idea of repeats are the key reason why the LCG is not enough by itself. Any questions about that? Okay. All right, so combined generators now exist that have a period of 3 times 10 to the 57 and still have uniformity and independence. So there's some really good random number generators out there. And if you go, now that you know to look for them, if you go into programs like MATLAB, like R, Python, you can actually change your random number generator behind the scenes. So for some reason, the random number generator that is used by default is creating weird artifacts in your particular sim, you can now switch to other random number generators that have maybe better properties. Maybe there's certain pros and cons of these different random number generators, but we don't now worry about uniformity and independence quite as much. We can now start worrying about other features and add those to our desired features and then switch between them. Okay. All right, so now we need to then open up this, and we're probably going to finish this up next time, but I'm going to try to get as far into this as we can, because now that we know that uniformity and independence are so important, and we have candidate random number generators that I claim have uniformity and independence, then as engineers, you should be asking, how do we know that for sure that there is uniformity and independence? So we need to know about the tests for uniformity and independence. And this is also stuff that can come up on the midterm. So how do we test for uniformity and independence? Let's start with uniformity. So statistically speaking, what we're saying is the null hypothesis is that any string of numbers presented to us, our default is assuming that they are from a uniform distribution. So that they have uniformity. That is our null. So we need then a statistical test that can detect deviations from the null or non-uniformity. We can detect non-uniformity. So we need to build that test. And so a failure to detect non-uniformity will end up, saying that maybe we have a uniform random number generator. But it might be that we just don't have enough numbers to detect it. Like if you only give me 3 draws, it might be uniform, it might not be. So we also want a test that can generate a conclusion for very small numbers of numbers. And so we're going to learn after the midterm, we refer to that as a high power test. And one of the tests that we talk about here is such a high power test. And we'll get to that. It's probably a test that'll be new to you. But the first test we'll use is a test that should be familiar to you from like 380 or 385. It's less power, but it works really well when you have enough numbers to detect non-uniformity. So here we're going to talk about our level of significance, alpha. we're going to usually set it to 0.05. That's interpreted as that if you give me a uniform source, I will improperly flag it for non-uniformity 5% of the time. That's our interpretation of that. All right, so how do we do this? Well, I mentioned at the top that the key prediction of the uniformity hypothesis is that if the interval is divided into subintervals, like faces of a die, finite number of subintervals of equal length, then the expected count in each subinterval should be equal and should be to this predicted amount of the number of draws divided by the number of subintervals. So we now need to build a statistical test about counts. So we're going to have count data. We're going to say you drew 100 numbers and we expect to see 10 in each one of these 10 bins to give us the 100 numbers. And so do we get a deviation from our count expectation? So what test is a test that specifically deals with expected counts of observations? So as a statistician, whenever you hear the word count, your head should immediately, like it's figuring out, like it's like figuring out as I put my right foot down, my left foot has to come up. Should be that quick. When you hear count, this test should pop up. Any guesses on what that test is? What was that? The chi-squared test. That's exactly right. So the chi-squared test is a test that's designed to test for frequencies. So you get a bunch of expected frequencies and a bunch of actual frequencies, and the chi-squared test tells you if there's a deviation from expectations. So chi-squared count. But we're going to learn that there is a better test to use for small sample sizes. So the basic process for the chi-squared test for uniformity, and we're going to make it more complicated after the midterm, but just for uniformity, this is how we do the chi-squared test, is that we divide the interval into a number of subintervals. On a midterm, I'll give you that number. I'll say, use the chi-squared test, or I may not tell you to use the chi-squared test, and you have to figure out that's the right one, but I'll tell you that, divide this into 5 subintervals. I'll give you the little n. So now after the midterm, you have to start figuring out how to choose that yourself. But for uniformity, I'll give you the little n. And so you choose the little n and you divide the whole interval by that little n. If the number of samples divided by that little n is less than 5, you cannot use this test. We'll talk about why mathematically this test fails to work in that case after the midterm. For now, just take that as a given, that if you see the big N over little n is less than 5, that expected count is less than 5, you can't use chi-squared. It just doesn't work. So, but if it's 5 or greater for every bin, then that's fine, we can move on. So then we count the number of observations, the frequency in each class, and then we compute this statistic. And this statistic here, after the midterm, we'll talk about where this comes from. It's not arbitrary. It's a little weird. Like if you're thinking in terms of units, it looks like the units shouldn't work out because you've got a squared in the top, but it's not squared in the bottom, in the denominator. So that seems weird, but we'll see why this formula comes up and what it means after the midterm. So for now, just take it for granted. It's a formula. This is probably one of those formulas that if you don't remember this formula, it's probably good to write down on a formula sheet in case I ask you to do a chi-squared test. I won't give you this formula. But this is the chi-squared statistic. And so O is the number of counts in each bin. E is the expected, which is just capital N divided by little n. And again, E is the number of expected. So you just do the difference from expectation squared divided by the expectation for every bin. And then you add all of those up across all your bins. And that's your chi-squared statistic. Higher is bad. Lower is good. Almost all of these statistics, the statistic is the different, not always, but almost all statistics you go with, the statistics is the difference from null, the amount of deviation. So when the chi-squared value is high, then you end up finding that it's more likely that you're going to reject the null hypothesis. So that's what we're saying down here. If you calculate this value, you then look up its critical level, its threshold in a table. I'll give you the chi-squared table. You don't have to write that down. I'll give you that on a midterm. And then if you compare the two, and if this statistic is greater than the critical value, then you reject the null hypothesis. You reject uniformity, and you claim these numbers, there's significant evidence that these numbers are non-uniform. That's the idea there. The degree of freedom that you use in this table, I think I don't know if you got that. Well, I'll show an example with the table. The degree of freedom you put into the table is the number of bins minus 1. So if I told you to divide it into 5 bins, in the table, you look in the degree of freedom 4 column, and we'll see an example of that. All right, so let's see an example of applying the whole thing. I give you these numbers. I could do this on a midterm. I could give you these 30 numbers. And then you divide it into these bins. So divide it into 4 bins, and then you're going to count. For all these numbers, how many numbers are in this bin? 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 How many times do people come in before 45? Okay. And then look so surprised that I'm standing here. I'm the same guy every Tuesday and Thursday. They come in and I stare at their little faces and they just look at me like deer in headlights, like, oh my God, there's a professor in here. Like I've never seen a professor at ASU. Anyways, I digress. There's 4 bins, and you want to count how many of these go into each one of these bins. And then that's going to give you these counts. So 3 went in that bin, 4 went in that bin, and so on. So we have our observed counts. Already, your spidey sense should be going off that this is probably not uniform because there's a huge number in one bin and a very small number in other bins. Okay, so then we calculate the expected value for each one of these 4 bins, and it's all 7.5. So that's the total number. So there were 30 divided by 4, 7.5. And so that's what we would expect under the null hypothesis. And then we calculate the statistic, all the observeds minus the expected squares divided by expected, summed across the bins. We get a value, 11.8. And then we compare that value to our table. Now we look at this table, and the columns of this table are a level of significance. So I'm almost always going to give you a 5% alpha, but I could give you a 2.5% alpha or a 10% alpha. But here it's a 5% alpha, this column, and I had 4 categories, 4 bins. So the degree of freedom is 3. We'll talk about what degree of freedom is after the midterm. We will get to that. But for now, it's just a formula. So 4 bins minus 1 gives me 3 degrees of freedom. And so that tells me that 7.81 is my threshold. So that means that's the most amount of difference from my null hypothesis I will tolerate, 7.81. I go above 7.81, I detect non-uniformity, and I reject the null. I reject uniformity, and I detect non-uniformity. So 11.8 is greater than 7.81, so we reject the null. That's how we apply the chi-squared. Yes? Yeah. Yep, you'll get a calculator, and I will even set up the little Canvas calculator as well in case you don't have a calculator next to you. Questions about that? And I'll try not to be too obnoxious about the numbers and things like that. When there's an ugly numerical calculation that whenever possible, I'll do calculations for you. Some of them, there's a limit to that. Like, you just have to, there's just no way I can do this for you. But this is not as bad as this. Like, if I were to ask you to take the mean of 30 numbers, I wouldn't ask you to take the mean of 30. I would just give you the mean. Like, I would just say on the side, that would be a hint. Like, by the way, this is the mean of the 30 numbers in case you need it. I would already do that. You don't need the mean for this, so I don't give you the mean for this. Okay. All right, and then I want to at least start this, and then we'll pick this up next time. So this question is, well, what if big N over little n is less than 5. We cannot use the chi-squared in that. We'll talk about why after the midterm. But there is a high-powered test we can use that just happens to not be great when n is very large. And that is the Kolmogorov-Smirnov test. And it's basically based on not binning the numbers, but sorting the numbers, thus the sorting hat. So the idea here, and I'll go into this in more detail next time, but the idea here is that you take your numbers. So here I only gave you 5 numbers. That's the blue row here. And it's too low for me to use a chi-squared because there's only 5 numbers. But can I detect non-uniformity a different way? Well, the thought is, well, what if I sort the numbers? If they're uniformly distributed and I sort them, then there's a certain range that I would expect them to be in if they were uniformly distributed. So if I sort them and there's 5 numbers, then I would expect the first number would be between 0 and 0.2. If I sort them and they're uniform, then the second number should be between 0.2 and 0.4, and so on. That's just the way. So basically, if I sort them, they should be close to this diagonal line. So but I actually plotted the sorted numbers here, and I can see that this stair step, this is what we call the sample CDF. This stair step is pretty close to the diagonal line, but it has some deviations. So this deviation, this number up here, the second number, is 0.26 from the diagonal line. In this table up here, that comes out where I can say it's 0.4 minus 0.14. That gives me my 0.26. So I can calculate the differences here. So this green number minus the blue number, that's what gives me that. The blue number minus the red, that's what gives me that. And so I can calculate all these differences, and the largest difference, that is my KS statistic, my Kolmogorov-Smirnov statistic. And so then there's a table in the back of the book. In this case, the degree of freedom is actually the number of data points. So in this case, it will be 5. But then you just look up the table and you compare that number to that table value. That is your KS. And so that's the idea here. I get this maximum value. I compare it to the table. So the table value says I can tolerate up to 0.565 difference. This is less than that. So I am not going to reject the null for this one, for this level of significance. So because it's less, uniformity is not rejected. But it might just be that I have a small number of samples. But as we'll learn after the midterm, the KS test is really sensitive. So if there's slight deviations from uniformity, it'll detect it. So because of that, it's not always the most appropriate test because everything is going to deviate. So once you have enough data, you'll be able to detect deviations from everything. And the KS test will just reject everything because nothing will be good enough. But for small numbers of samples, it works really well. All right, that's where I'll stop and we'll pick up next time. I want to give you guys an opportunity for clicker credits. So poll here. All right, so question here is, what is the minimum number of expected counts in each bin for the chi-squared test to be able to be used? So there's an expected count for every bin in a chi-squared test in order for us to be able to use the chi-squared test. What is that number? That it needs to be this number or higher. So I'm looking for a number here. I guess I could have used numeric, but is it 0? Is it 1? Is it 2? What is it? And that's all I've got for you. So we'll see you on Tuesday. Have a good weekend.